So now we're coming down to the issue. I'm going to zoom in over here and we're going to look at these two atoms. So this right here, this is the situation where there are no lone pairs, there's no difference. And the shape here, it's this triangle shape. And when you put this in some kind of instrument that measures and looks at the atom, it will see, 1, 2, 3 bonds, and it will turn out having this trigonal planar shape. However, if you have a lone pair, like right here, this one has a lone pair, you can tell just looking at this, these are not the same shapes. You can tell that this one, well, obviously has less atoms in it, right? And then you can also tell that, or maybe you can tell that this distance, it's a little bit less. What the electrons do when they're in this atom is they get a little pushy about stuff. And these electrons want not just the space that we might designate them for, but they also want this space and this space. And so they actually will start to kind of push these atoms a little bit closer to each other. They're very pushy like that. So it doesn't change it by a lot. It may only change it by like a very, very small, like a few degrees. But it's something. It does change it. So this is valence shell electron pair repulsion. These electrons, they spread out. They take up all of the space above the atom. And when you look at it, and again, you can just see this with your own eye, you can tell that the lower structure does not look like the top structure. And again, when we put things in instruments, they look and they can see the bonds, they can, not the bonds, but they can see the atoms. And sometimes they can see the motion of the bonds. Some types of instruments look for the bond motion, and there's characteristic bond motions that are associated. There's a lot of ways that we go about figuring out if things are double or single or triple bonds. But the atoms right here, they do look different. There's nothing sticking up here. That's why we had this new naming style come up. So we're going to come over here and we're going to work our way down through the first section. The molecular geometry only matters when we've got the lone pairs. So here's our first situation with the lone pairs. So notice in this atom, we have 3 bonds, we have 1 lone pair. So let's go over here. We need something that has 3 bonds and 1 lone pair. 3 bonds, 3 bonding regions, 1 lone pair. So our tetrahedral shape here, I think it's easiest to imagine that this is what's replaced with the lone pair, or think of it like that's the part that disappears. And so our name is going to be trigonal pyramidal. Let me scooch this over. And what we're saying is that this is the predicted electron geometry structure. And when you replace the bonding atom with a lone pair, which isn't really seen in the atom, in the spectrometer, it's not really seen in the equipment that we have. The equipment is looking at the atoms themselves. They do look different. The reason that we call it a pyramid is because if you imagine this being a triangular base, this is 3D. So this is kind of like something that you could sit flat on this page, and it all comes up to this middle atom. You can kind of see that. It looks like a triangle-based pyramid. So trigonal pyramidal. It's definitely not flat. So trigonal pyramidal. And keep your trigonal straight because there's the trigonal planar too. And there's another pyramid later. We had already talked about trigonal bipyramidal. So keep the difference between trigonal pyramidal and trigonal bipyramidal in your head. This one only has 3 bonds. This one has, it's this one. This one has 5 bonds. And then now we have a situation where we have 2 pairs of electrons, and so it looks like this. And this name always makes a lot of sense to me. It's just bent. And again, 2 bonds, 2 lone pairs, bent. And let's look on. So trigonal bipyramidal, that's this category here. And in this one's case, we have 4 bonds and 1 lone pair. So this is seesaw, and this one is a lot of fun. If you have a model, you can see it. But right here, this is the original structure it's being built out of, except that you're missing you can think of it that one, or you're missing this one. And when you look at it, you kind of turn it sideways, it looks like there's a little seesaw that some kids can play on and go back and forth. That's a fun one. Then after that, where the electrons come off, and I should make a note, or where they replace electrons, replace atoms on the triangle. We call this equatorial, not axial. So they'll replace this one, and then this one, and then this one before they'll replace the top and the bottom. So it's like it crossed out this one, and it went sideways to make this structure. And then like if you cross out another one, like this one here, you end up with this kind of a shape. It's a T shape. Again, notice this has 3 bonds and 2 lone pairs. And then finally we have 2 bonds and 3 lone pairs over here. And that one turns out to be linear. Yeah, there's more than one way to get to linear. Finally, the last 2, this one has 5 bonds and 2 lone pairs, 1 lone pair. And that one is square pyramidal. You look over here, this looks like a square-based pyramid. That's why it's square pyramidal. And then lastly, this is actually a square that's in a plane. So this is square planar. So now go ahead on the remaining ones, there's only 3, and figure those ones out.